So this talk is the top 10 web hacks of 2014. So how many of you have seen this presentation or one in previous years before? A handful of you? No? Just Jim? Okay, so we're going to talk a little bit about what that is, right? So every year there's just an absolutely massive pile of security research that we have to have. There's a security conference literally every day of the year. There's a calendar somewhere that there's some security conference everywhere in the world sharing research. And so this massive pile every year, we try to, at White Hat, we try to consolidate a list that is all community. The community submits the new web hacking research of the year, submits it to us, and we put it up on our blog, and the community votes on it. We open it up, we'll have something like 80 new techniques or 100 new techniques, and the community will vote on it, and we'll narrow that down to a top 15. We'll take that top 15 to a panel of application security experts that graciously give us their time, and they will be the final say on the top 10 and order it. So basically this is kind of like the cliff notes of all the really cool application security research that happened for the last year. So these are, just to give an idea, this is some of our previous years, right? So the top number is the total number of techniques that we got, and then the bottom you can see the winner. So you guys will recognize things like Beast and Crime. These were big SSL attacks that were Black Hat talks in the past couple of years. You can go all the way back to Shockwave XSS attacks and GIFAR, which was a really fun one in 2008 that was everywhere. So you guys probably heard about all this stuff. So you can kind of see a trend of encryption attacks are always very highly regarded. People really always like that research. Last year, a new XSS technique by our friend Mario took the top slot, but 3 of the top 5 was still encryption related, so people still really like encryption research. So this is this year's top 10, the 2014 top 10. That was based on, like I said, the community vote and everything like that. So encryption took the number 1 again with Heartbleed. I think there was no surprise there. The first attack with its own marketing campaign and a logo and all that kind of stuff. I've never seen something like that before. And then you guys will probably recognize some of these other ones. So what we're going to do here, we only have about 45, 50 minutes to talk to you guys. So we don't have time to go into each of these. Most of them have an hour-long talk just for themselves, right? So we're going to just kind of give you the highlights of 10 through 6, and then we're going to kind of try to deep dive for the top 5, since they seem to be the most interesting, and we'll try to give you everything that's important to know about them. Again, if you're interested in any one of these, go find the hour-long talk about it by the researchers who actually did the research, and I'm sure you'll find a bunch more stuff.
Yeah, so again, before we start with the top 10, like he said, we're going to be really pressed for time here, covering a lot of material very quickly. So if I speak too fast, just grab something, throw it at me. You can also find us floating around the conference for any questions afterwards. So starting with number 10, we have covert timing channels. Now, a covert timing channel is essentially a side channel attack, or a timing attack in measuring how long it takes for a system to perform some action. This particular research covered caching headers and the amount of time necessary to possibly dictate if you could tell, based on just response time alone, if an item had been cached or not. This particular research, they covered various HTTP cache headers, like last modified and E-tag for request headers. And for the response headers, they looked at if modified sense, if unmodified sense, if match, if non-match, and if range. So a lot of real heavy math went into this, and this made our number 10. Now, this was one of the first talks where a group of people actually kind of petitioned to be in this top 10 list. So when they put this talk out, they had a little disclaimer saying, yes, we hope to make the top 10 web hacks list of next year. And sure enough, they made the final list and got voted into number 10. So congratulations to them.
Yeah, we've never seen someone campaign to get on our list before, so that was fun, right? So apparently it worked. So number 9, this one was kind of interesting. It was a pretty traditional denial of service attack. But the avenue of attack was what was really unique about it. So this researcher was able to find a way to create a note on Facebook, like Facebook has some notes feature, and then the denial of service attack would it was an HTTP GET flood just with requesting a bunch of images over and over, and the attack actually looked like it was originating from Facebook. So it was kind of, you couldn't really attribute the denial of service attack if you were the victim website being DOSed. you didn't know where it was coming from. Well, you knew where it was coming from, and it was coming from Facebook. You didn't know the person behind the attack. So that was super interesting.
Cool. Now, number 8 is an Apache 2 struts class loader remote code execution. And what's kind of awesome about this is that this particular researcher got not 1, not 2, but 3 CVEs out of this remote code execution. And mainly got that because the improper fix was implemented each time. So what you could do here is basically you could pass any kind of system command to a class.classLoader reference if it was part of a .action URL, and it would be treated as actual executable code. So he reported it, and they added to the exclude params list of struts2, blocking class.classLoader only. Then he changed that from dot notation to bracket notation, right there on the right, which awarded him yet another CVE, because that was their fix. He broke it again. He let them push that fix to live before reporting it. So they blocked that as well. Then they also forgot that you could actually do an uppercase class loader for the C again. So again, 3 very silly CVEs, but they are CVEs from one particular remote code execution. It's pretty funny.
It's a quick boost to your resume, right?
Yeah.
Not 1, 3. Same vuln. Okay, so number 7, this one was also kind of unique to make our list because this one isn't attributed to any one researcher or attacker or anything like that. This one is actually the anonymous hacker, right? So this is, generally we just saw a huge uptick in this in 2014 of a trend of mostly journalists and reporters getting attacked and their social media credentials being taken over and things like that. And that's what the story that made Wired.com was the one that got all the attention to get this one on our list, and it got voted pretty high. Was a Google two-factor authentication bypass, not using the app, not using the Google Authenticator app, but when SMS version of the token. If a text message token was coming to your phone, what people were doing were social engineering, calling and social engineering the cell phone providers and getting a text forwarding set up so that I was forwarding your text messages to my phone. You were also getting them, but they were also being forwarded to my phone. And that way he can get, the attacker could get a SMS token of your two-factor thing, and a big journalist got, a Google account got attacked this way. And then once his Google account got attacked, the attacker went and reset all of his passwords for all his other stuff because he had access to his email and took over his entire online persona, which we saw this a few times in the past few years. So cool that it made the list.
So moving on to number 6, we have hacking PayPal accounts with one click. Real quick, are there any bug bounty hunters or people that participate in responsible disclosure here at all?
A few, yeah.
I see 1 or 2. Okay, cool. Well, if you're not familiar with it, bug bounties are a program where most websites allow you to openly hack them, so long as you do a couple things. You report the vulnerability to them, you don't disclose it publicly, and then maybe they will not pursue legal action against you. Typically, they don't if you act in good faith. This is the first time that a single bug bounty actually made our list. Typically, it's new and unique hacking methodologies. This one's really cool. Again, another quick precursor. Does everyone here know what CSRF is, or cross-site request forgery? A couple people? Okay. For those that don't, all it is basically is a way to force someone to do something on a website that they would otherwise not do. And it's not due to any kind of real user error, it's due to an implementation error on the website. So you as a victim can really do nothing wrong aside from clicking a link, but there's other ways to make someone exploit that anyways. So what's going on here? He found a site-wide cross-site request forgery bypass. Typically, with cross-site request forgery, the fix to it is to have a token, a unique token that comes with you on every request that you send, and it changes every time you've used the previous token. So say you want to change your password, the form that you're sending that password from has a one-time use token with it that gets sent to the server validates that the token hasn't been used before and was sent to you on the previous request. Password is changed. On that next response back from the server, a new token is sent to you. So this way someone else can't just forge a request for you to make because they're not going to be able to successfully guess that token, or they shouldn't be able to. What was going on with PayPal here is that they were using the same token per account. So say you yourself, your username, had a CSRF token that was associated with it and it was not changing per request, or by logging out and logging in. Now what he found is that he performed some authenticated requests, like transferring money. When he removed his session tokens from the request, it redirected him to a login page. On that login page, he put in a victim's email account. So say, I'm the attacker, I know his email address. I supplied his email address purposely with the wrong password. And then that response came back with the CSRF token valid for that particular user's account. Once you have that token, you can craft requests to do anything within context of the website. Change password, delete account, transfer funds, all the good stuff. And PayPal actually awarded him a $10,000 or US dollar bug bounty for responsibly disclosing this. Pretty cool hack.
Okay, so those are the quick ones. That was quick. I don't know, right? From 5 on, we're gonna actually get into these a little bit. Okay. So number 5 was the misfortune cookie attack. Did anyone hear about this? It kind of made big headlines a little bit. Okay. So the misfortune cookie attack. What it was these researchers were able to target and take over routers, but not just routers, residential gateway routers. So the router that's in control of an entire neighborhood of computers or something like that, with just one HTTP packet, just one HTTP request with some cookies in it. And we're going to get into how. It was actually a pretty interesting talk. Again, this is probably my favorite one on the entire list. It has one of the best hour-long talks I've ever seen on this kind of topic. So if you're interested in this, go watch the hour-long talk. So a little bit of background of things that you need to understand before you can really understand this attack. This was all new to me when I was doing this research too. I didn't really understand how a lot of this worked. So there is this specification in this protocol, this TR69 protocol. If you've ever called up your internet service provider and had some problems with your modem or your router at home, and they can do something remotely, they can make it turn off and on again. They can control some things from their end. This is the protocol that's being used. And so that's a lot of power for someone else that's not on your network to have, right? They can access and change settings on your firewall internally, your router internally. And so these researchers looked at that and said, hey, that's a lot of power. I want to focus on this. And so the way that it works is there's this auto configuration server, an ACS, that there is going to be some sort of authentication, some dual authentication back and forth here between the router and this server. Basically so that this server knows that it's talking to the router that it thinks it's talking to, and that the router knows that it's talking to a valid ACS on the other end, so that it's not just some person pretending to be an ACS and trying to make changes on this router, right? And so there's a whole bunch of magic on the back end of the ACS that'll do some stuff that's not really important for this part. And then on the right-hand side, this is your consumer premises. This is your devices that are connected to your wireless router, or like I said, a residential gateway router, which is even scarier. So this protocol is about 10 years old, 11 years old. 2004 it was written. It uses SOAP RPC, which is just XML. Over HTTP. So again, for us web hackers, you see something with all this power like an ACS, and it uses HTTP, and you start drooling profusely and saying, okay, I'm going to target that. So that's what they did. So they said, okay, this ACS, this is a single point of failure. This is a house of cards waiting to fall over if I can figure out how to attack it, right? So this TR69, this consumer premises protocol that was just described on the last slide, it runs on port 7547, which with a scan of about 2.15 million hosts, this was done by, the University of Michigan. This port was the second most popular port open on the internet, with just over 1% of the 2.15 million. Rapid7 actually took it a step further and did scan the entire internet, not just 2 million. And this number was actually a little small. It was actually 1.18%. So it's about 46 million devices, Internet of Things devices, on the internet with this port open through 189 countries. Some of those countries, over half of the IP addresses in the country actually had this port running, and you'll see it's going to be bad because it was vulnerable. So what's running on this port? Okay, so this port is open on millions of devices. What's behind that port? So it's this. There's all these different. There's a few different technologies that are going to run this protocol, but overwhelmingly, 52% of them use this firmware called ROM pager. I had never heard of this, so I had to go digging into it, and the researchers dug into it a bit. And they said, okay, I'm going to focus my research on that big slice of the pie, because 46 million devices have it, and 52% of them, right? We still have millions and millions of devices running ROM pager. So if I find a problem in ROM pager, I can kind of roll around in my vulnerabilities. When we looked at a little bit deeper and said, okay, which version numbers of these firmwares are running on these devices, it turned out that over 98% of the ROM pager versions running on this port were actually all one single version, this version 4.07 of ROM pager. This is the part in the talk where I like to play guess what year that was written in. It was, what was this one? 2002. So this firmware is just a little old. It's about 8 or 9 versions out of date. And yeah, this stuff is absolutely everywhere. Millions and millions of devices are running ROM pager from 2002. Over a whole bunch of different brands of routers and stuff like that. It's not just one single brand of router. So, all right, cool. That's all the background. Get to the hack already, right? So, for those of you familiar with things like buffer overflows, this is what they did. They said, okay, let's fuzz this firmware. I have got my router. It's running ROM pager version 4.07, like millions of other devices on the web. Let me do some fuzzing. And so, just with changing an HTTP header, there was an authorization header that was being used. And then they just put this digest username, and they just put A 600 times, 600 A's, and the router crashes. And they say, okay, I did something, right? For those of you familiar with buffer overflows, that's okay, something happened. And they did some digging into the code that was running on it, and eventually found it was just this unprotected string copy that was doing that from that header. But there was no debugger available to them. So they couldn't actually see the core dump and actually see the memory stack and try to figure out where they were going to try to take control of the router. So they wrote their own debugger. They actually cracked open the router, the plastic on the router, and they soldered into the motherboard, and they wrote their own debugger, which is the coolest thing that's in this presentation. So for those of you who are Power Ranger fans, they named it Zordon, was the name of their debugger. It's a forced acronym, and I don't remember what it stands for. But they actually soldered into it. They got their core dump. They see the instruction pointer at the top, and now, okay, they can start to write their exploit of their buffer overflow. They had to take it one step further, though, because this wasn't reliably exploitable over the internet, because depending on which router manufacturer made the device, the memory layout was slightly different. So they weren't sure where in memory that their attack was landing to get into this instruction pointer to actually exploit the attack. They could exploit, a percentage of them based on which brand router it was, but there was over 200 brands, and so the number of exploited devices would have been pretty small. So instead of just that authorization header, they took a look at the cookies. These devices actually use cookies since it's all just over HTTP, and the cookies were actually pre-allocated memory stack, so they knew exactly where in memory they were going to be, and the naming convention was just like C0, C1, C2, C3, and the pointer in memory, again, this pre-allocated memory space, was just whatever number came after the C. If you took the C off, it was just 1, 2, 3. So they knew exactly where they were landing in memory with the name of the cookie. So just by malforming the name of the cookie, you could see on the bottom, this C100737, this whole thing, they knew exactly where that was going to land in memory. And this was basically changing the path. So they chose, oh my God, lead hacks, because as one does. And this was, it redirected the user of the router interface to this path, oh my God, lead hacks, which was not found for some reason, right? They didn't have a path named that. So they actually demonstrated in their talk that with, I think it was 3 cookies, 3 or 4 cookies. They didn't show the cookies because it was a little dangerous to show an audience this, but with 3 or 4 cookies, they were able to completely bypass the authentication of the router. So just sending one request with 3 malformed cookies, they were admin on the router and they could do whatever they want. Again, these could be routers with hundreds of devices behind them in a neighborhood, residential gateway routers. And yeah, 50% of certain countries were vulnerable to that. So this was very scary. This is usually the slide where I try to make everyone feel a lot better about this, about how to protect yourself. This one, it's kind of hard. This one, the only way to really protect yourself if you have a router that's vulnerable to this is to just flash the firmware and install new firmware that's not vulnerable. And a technical crowd at a conference like this, that might be an okay solution. I'm not going to be on the phone with my grandma trying to walk her through flashing her firmware anytime soon. I don't know about you guys. They actually maintain a list here at the bottom. If you're interested, there's a URL right here, a list that they maintain that are vulnerable routers to this. They did the demonstration live on stage where they took the plastic off the box of a router that they just bought off the shelf and were able to bypass the authentication. So it's a ton of this stuff. They're still being sold. It's really just a supply chain problem. The manufacturers are just putting old firmware on these devices. So Super cool stuff.
Cool, thanks, Matt. So at number 4, we have Rosetta Flash. Now, if any web app hackers tend to be here, you've probably seen callbacks before, JSONP responses. Now, what Rosetta Flash is it's a tool that will allow you to transform a binary SWIFT or Flash file into completely alphanumeric Flash.
And he has a monkey, so we had to put him on the list.
Sweet monkey.
Right? Yeah.
So again, it's the name of his tool. So when you have a binary SWIFT, actually I think the next slide has it. There we go. So this is what a binary SWIFT would typically look like if you look at the kind of garbage on the right-hand side. Now, a JSONP callback response will only accept a certain character set. Uppercase, lowercase letters, numbers, well, no, not numbers, underscores, and periods. Now, you can't feed a binary input to this, obviously, because it's not going to work. But with JSONP, we can actually force the SWIFT to execute if we actually had an alphanumeric version that was syntactically correct. And this is what this particular research went into. It's Michelle Spagnuolo, I believe.
Mikhail, yeah.
Yeah. Basically created a tool that will just transform a binary SWIFT into completely alphanumeric. Now, there's a lot of sites that are using JSONP at the time, like just a handful. Google, Twitter, LinkedIn, GitHub.
You've heard a few of these.
And when we say Google, it's not like some third-party acquisition. This is like www.google.com, accounts.google, maps.google, drive.google, et cetera, et cetera. So before we get into this, let's take a look at the Swift header formats. So all of them kind of start off with a particular magic byte or a signature, followed by a version number, the file size, and then depending on if you're using a form of compression or no compression at all, the structure changes a little bit. For the purpose of this research, we're going to dig into the zlib compression, because there are a couple things that need to happen in order to actually exploit this. The first 2 bytes have to be guessed correctly, as well as a proper brute force of the Adler32 checksum that's going to verify the integrity of that compression. Now, Rosetta Flash, the tool that he created, is going to use ad hoc Huffman encoders in order to map non-allowed bytes into allowed ones. So the Huffman encoders are effectively going to act as a Rosetta Stone to translate this binary garbage into readable data. So we don't have time to go into all the technical details for this, sadly, but like we said, this is an hour-long talk, and his information is extremely in-depth. So I highly recommend that everyone check that out. So this is his proof of concept exploit code, just a little bit of action script on the left-hand side, and this is what it transforms to in just the alphanumeric tool, whereas before it was all that binary garbage. And then this is how the exploit would actually go down. You could embed this particular payload into an object tag with the data attribute. You would specify the vulnerable endpoint at the top, and then in flash vars down there in the bottom in the param tag, you would specify, again, the vulnerable website that you're going to be going to, and then an attacker-hosted site where you can then log this data that's going to be transformed back and forth.
So the gist of what's happening here, right, is that you are executing your Flash file that you wrote in the context of something like google.com.
Mm-hmm.
So you can, anything that with the user's cookies. So if the user you're attacking has their cookies in their browser, they're going to execute your code in their browser with their cookies. That anything that that Flash has access to on that site, right? In Google, it could be a lot of things, and you can pull all of that information out and send it back to you, right? So you're just exfiltrating data that this user is protected by this user's, authorization.
Yeah, running in the scope of the target domain. Now, mitigations to this, a couple different ways you can fix it. With web app hackers, there's typically a bunch of things we can do with cool response headers. So one, we can obviously not use JSONP on sensitive domains. You can sandbox that content off so where those cookies aren't accessing the same content. You can also add a content disposition attachment file name header to the response, which is going to effectively download the SWIFT instead of allow it to run in the context of that browser. You can also add X content type options no sniff, which will disable content sniffing. Now, the typical response that comes back from this is going to be an X shockwave flash header. But with no sniff, or by forcing it to be application JSON or application JS, or JavaScript, then obviously this is not going to run in the context of a Swift file. It's going to run as JavaScript. Another thing you can do, if you look at the commit history right here, the little green text right there that starts a comment bracket, that's what the likes of GitHub, Google, Twitter did to fix this. Because by adding those characters, if you remember the allowed character sets, it can only be upper or lowercase letters, underscores, and periods. That's not going to be valid. So now even if you have that Swift payload in there, it's not going to fire. But it's still syntactically correct for JavaScript. So the actual JavaScript that was intended to be used there is going to work.
You no longer control those first 2 bytes, which were very important in order to make a valid Swift file. So cool. So that one, if you guys are interested in that, how many people were at AppSec EU in Amsterdam last week? A few of us followed. Yeah, a few of you followed down. He actually gave the hour-long talk about that at AppSec, so there'll be a video of that available. He goes into some pretty deep math on how he makes a Swift valid, and it's more complicated than we just got into. We gave it the highlights. Okay. Yeah. So number 3, Poodle. Poodle was another one of these vulnerabilities that came out this year that all had branding and logos and a cool name that's really catchy, so it probably made the news, and it followed suit in some other predecessors. But what Poodle is at the heart is a SSL downgrade attack, right? So it's forcing your browser to use a older version of SSL that was vulnerable to this thing that is Poodle. So we're going to get into a little bit about how SSL works and this encryption works, because this old version of SSL, because it's kind of important. So SSL's magic. All right, moving on. No, I'm just kidding. So yeah, you're going to take some plain text, you're going to take a key, you're going to do some magic, some encryption going on, and you're going to come up with some ciphertext on the other side, right? So in what we're focusing on now, though, is SSL version 3. Which is what Poodle breaks. And SSL version 3 came out when?
1998.
1998. SSL version 3 came out, and certain websites still need to support it because Internet Explorer 6 still exists on parts of the internet, and Internet Explorer 6 does not support anything over SSL version 3, unless you do some cool tweaks and stuff, which again, I'm not calling grandma and trying to tell her how to turn on TLS on her Internet Explorer install. But if I was a good grandson, I would just install Firefox or something like that, right? So, okay, so how does SSL version 3 work, right? So we're going to have our HTTP request, right? It's going to be some sensitive data that we're worried about, right? Some session cookies, some CSRF tokens, things like that. The first thing that happens in SSL version 3 is that takes that sensitive data and attaches a MAC to it. All right, so this MAC is going to basically act as a checksum that if this is ever tampered with, that the computer on the receiving end, the server on the receiving end is going to know that something was tampered with, and it's going to know that it's no good. It's going to drop the request, right? So this is all the MAC is used for, right? And then there's going to be some padding, right? So it's going to be sensitive data. We're going to have this MAC, which is like a checksum. Then we're going to have this padding. So different algorithms are going to use different size paddings, right? So things like which is which? I always forget. DES is 8 bytes. The padding has to be a multiple of 8 bytes, and AES is going to be blocks of 16 bytes as far as this padding goes. All right, so this padding is kind of important in this attack, and you'll see why in a second, but what we're really focused on is that very last character in the padding. All right, so it's going to be a bunch of pseudo-random information, but then that last character is actually going to tell you what the size of the padding is. So it's going to tell the computer on the receiving end, okay, if I go back so many bytes, I'll find the MAC, which I can then validate, and then I can find the sensitive data, right? So that last character is the size, and that's what we're going to be worried about. And in this version of SSL version 3 that is being attacked here, they're using the CBC, or cipher block chaining mode algorithm. Okay, so how does CBC work? So again, we have this whole, phone call happening, and then we have this whole whole sensitive data MAC thing, right? And in CBC, we're going to break this up into chunks. Again, either 6 or 18 chunks at the end there, and then these chunks are going to be exclusive OR. They're going to be XORed all the way down the line. And then during encryption, it's going to travel to the right here in our little diagram. And so it makes sense when you're decrypting this, you're going to start at the back and you're going to work the other way, right? So in this attack, what we're really worried about here is that if you're going to modify anything, this MAC is going to fail, right? So then the server knows that something's up. So say someone's man-in-the-middling this traffic. Right, what they're going to do is they're going to take one CBC block at the beginning somewhere at the beginning of the HTTP request, because that's usually where some of the sensitive data that you're trying to steal is, things like cookies. You're going to take that block that's already encrypted. You're going to move it to the end, which is part of the padding, right? And so logic says, well, that's going to fail, and the HTTP request is going to be dropped because it's been tampered with. The MAC is probably not going to go through, but every once in a while it doesn't. Because that last character, right, that denotes the size of the padding, every once in a while you just get lucky and that character matches up, the MAC stays the same, you're all good, and the HTTP request goes through. So it's about 1 in every 256 times. So it's actually not that many times, right? In the grand scheme of how fast computers can make these requests, it's not that bad. But what this denotes to you, what this tells you, is it just gives you that last character. Now you know what that last character of that encrypted block is. So 1 in every 256 times, you can steal 1 character of encrypted data. So this is kind of, okay, now it gets a lot bigger, right? Okay, great, it's a lot of work and I did 1 character. But with things like JavaScript, you can force thousands of requests to happen, no problem, and start to steal this stuff. It's kind of easy to defend against if you're on the other side, right? Hey, I see thousands and thousands of requests coming through from the same person. Let's cut this off. But this is an SSL3 vulnerability, right? So why are we worried about it, right? We're all using TLS, I'm sure, right? Websites that we use are using TLS. Well, it was actually possible in modern browsers to force them to downgrade. If the web server accepted SSL version 3, you could force the victim that you were using to downgrade to SSL version 3, and then you can execute this attack. Obviously, things like TLS at the handshake and all this kind of stuff is not vulnerable to any of this. So I kind of went through some of this, right? But the requirements, a motivated attacker, because this is going to take thousands of requests. You need to be motivated, and you're going to get 1 character at a time, so you got to be really motivated. This web server is going to need to just be okay with you sending thousands of requests at it over and over again while you're decrypting encrypted traffic. But the solution is pretty easy. Don't support SSL version 3. You might make some users who are using Internet Explorer 6 unhappy. I say, screw those users. You don't want them anyway. Just disable SSL version 3 on both client and server. And then also the CBC-based algorithm is vulnerable to Poodle. It's also vulnerable to other things like Beast and Crime from previous years. So moving away from that is wise also. There are correct ways to implement it, but it's actually harder to do those things, and it's easier to just move away from it, move away from it altogether. Oh, our co-presenter Jim Manico, everybody. I'm sorry, yes. No.
How good are clients like Safari and other browsers good at disabling SSL3?
Yeah, I mean, it's just not going to, the best way to do it is on the server, right? Just trying to do that on a client is much harder, right? So
actually with Chrome and Firefox, you can do it in the about config settings quite easily. Another fun fact, in October of 2014 last year, Microsoft actually came out with an option for you to enable TLS 1.0 support on Internet Explorer 6. However, users that use Internet Explorer 6, like you just said, are typically the ones that don't really care about encryption, or they don't really grasp the severity of why they need to use SSL.
They're not going to find that setting buried deep into the Internet Explorer encryption things.
Cool. So moving on to more branded vulnerabilities, we have ShellShock. Now, I'm sure you guys have heard about this one, right?
I hope.
Yeah. I feel like half of you exploit it daily. Okay. So ShellShock is a remote code execution that's targeting the Unix bash shell. It's extremely easy to execute, extremely easy to exploit, and you don't really need to know too much code to get anywhere with it, really. From one single unauthenticated request, you're basically granted a shell if you're using this vulnerable version of bash. Talking about software that's several years old, who knows how long bash has been able to be exploited for in this way for ShellShock? Any guess?
20 years.
More than that.
25.
25,
yeah.
Yes. So for 25 years, this has probably been being executed in the wild, if anyone knew about it. And typically, it's a security researcher of some sort that comes forward and says, hey, I think this is working improperly or whatever. This wasn't a security researcher. This was someone who just stumbled across it. And if you're looking at like the report trail, he's just like, yeah, I found this really weird error here, and I think it's been like this for a long time. And then, of course, this set the internet up in
you can actually see the thread where he reported.
Storm.
He's like, I think I found something that might be interesting. Yeah, you did.
Yeah. Funnily enough, the only thing harder than exploiting ShellShock is probably just explaining it to the public. It's extremely easy to exploit, and we'll start digging into that. So just a little bit of history. There's a guy who goes by Errata Rob, who did a lot of really awesome research on this the day it came out. It's like within hours, he was already delivering live statistics about it. This is an open source tool that he uses that he built called MassCan. And it's very simple. You supply a target IP address, a port, banners equals true allows cookies to go with the request. And what he has here is just a benign example. Now, I'll get into more about how the exploit actually works in a later slide. But if you look at the user agent, cookies, host, and referrer header, he's setting a small arbitrary payload that will ping a destination that he supplies. And then you can see like a dummy HTTP request down there. So what do you expect to happen once this request is made to the server? Well, it's going to call back to you. So here's some Watershark traffic of all these particular IPs just calling back to him, pinging him a couple times after just sweeping the internet, just scanning, just making an HTTP request to a random host with that particular injection, again, in just the user agent, cookies, host, refer, wherever you can really supply input. But that's an easy unauthenticated request to make to a domain. Now, before we get into all this, before we had fancy GUIs, a little bit of history. Before we had pretty interfaces, we had the command line. It allows us to communicate the system via text. We can actually do things like who's logged in, create a file, give me some directories, delete absolutely everything on the file system. Yes, I'm sure, don't need confirmation in just 8 characters. Now, really think about that for a moment. You can completely destroy a file system in just 8 characters. So when we're in a world where like our injections are sometimes limited by character length or like the length of the payload, this is really convenient. Really convenient. Now, the vulnerability itself lies in the ability to arbitrarily define an environment variable within a bash shell, which specifies a function definition. Now, the problem is that after executing the function definition, bash is going to continue executing the code after that as if it was actual code, so just like a regular command injection. At the time that this came out, roughly half the servers on the internet, or probably still, are running Apache. And Apache will process CGI scripts. CGI scripts are processed in bash. So just by making a regular HTTP request to that server, if a CGI script is processing the request saying, hey, who sent this, what's the refer, what cookies are available, that's where the payload, that's where that ping command got executed. So then this next question is, how do you get a system to arbitrarily run this? Well, you can just make a request to it. But now the other question is, why does a web server actually run these bash commands? And you have to, looking at a little bit of history, the AT&T Bell system in the 1970s kind of started the inspiration for modern web servers. Use one program that talks to smaller, simpler programs so you don't have to write them all yourself. For instance, if you're going to parse or look through a file for a particular string, you're not going to write a parser yourself. You're going to use awk or grep or some other tool that's already out there. The building blocks of coding is for us to use smaller chunks of code that someone else has already invented. Do not reinvent the wheel. We've heard that over and over and over again. So you have program A that talks to smaller programs, B, C, D, and E, all without being displayed on the screen, but running in some background process, usually the bash shell. Now, this isn't just web servers as well. Internet of Things devices are also running bash. Your phone might be running bash in some sort. If you have a Wi-Fi enabled dog feeder at home, it's probably running bash. If for some reason your Wi-Fi connected toaster needs to talk to your Wi-Fi refrigerator, these are all, and the running bash, these are all equivalent hosts to be part of like a ShellShock botnet, if you wanted to, a ShellShock slave. Whoops, skip forward a little bit. So it's something as simple as like this, We can incorporate a string in there. We know that strings should not be treated as text. A simple escape down there, and then whatever command is after the function definition is going to be executed by bash as code. Pretty cool, right? Really easy, really severe. It's harder to explain it to someone than actually exploit it, because that's all you need. And then this guy actually has a shirt that he wears where, and this would have been really cool. So whoever found this, obvious potential to just worm the entire internet. The next time someone finds something like this, I urge you all, worm a patch.
So my t-shirt is one of my new favorite t-shirts. It actually says, my user agent is, and then it's a ShellShock exploit that patches ShellShock. It updates to itself. So there's it.
If you want to be immortalized on the web for security, that's what you want to do. Find some mass wormable injection, and actually, before you just unleash a patch on everyone. By the way, you guys are all vulnerable. You're welcome. You're fixed. Now, number 1 is Heartbleed. Again, show of hands. Who all's heard of Heartbleed? A lot more people this time. Now, Heartbleed, again, fancy logo, a little bit of marketing behind it. It was vulnerable in the Heartbeat extension of OpenSSL. And it's only vulnerable in servers that are running that particular version up to 1.0.1f, which was released in January 6th of this past year. Completely untraceable attack that allows you to read arbitrary memory from the server. And it comes from a maliciously crafted Heartbeat request, which is user-controlled. We can control the data that's being sent there. This is also the first vulnerability that we really saw this year, or this last year, that had branding attached to it. For once, security vulnerabilities were really kind of getting out of the echo chamber. You're seeing this little Heartbleed logo on news stations and world news outlets. I guess it took a pretty logo with blood dripping on it for some reason to grab someone's attention. But at the time of this being publicly released, nearly 500,000 of active, secure, SSL-supported websites were vulnerable to this arbitrary memory read exploit. So again, just some quick Netcraft statistics. At the time this came out, more than half the websites out there were Apache, with the second busiest being Nginx. Now, if you're looking at active sites, Microsoft IIS server is kind of up there. Now, IIS server, although it's the third most used, it's not by itself vulnerable to Heartbleed because they use Microsoft's S-channel implementation of the Heartbleed extension. It's not exactly vulnerable, but that doesn't mean that IIS servers itself aren't vulnerable as well, because you could be using an Nginx load balancer or HA proxy or something in between that can still be vulnerable to this attack when wrong versions of OpenSSL are being used. So the flaw right here just simply results from an insecure memory allocation. We have, and this is the actual code that was in there, you have a payload and a padding that's being tainted directly from user input with no bound checks, no sanitation done at all. And it's funny enough that this commit actually happened about 1 or 1.5 hours before New Year's Eve of 2012. So whichever developer was developing this, he was probably more interested in going out and shooting off fireworks and drinking, and just wanted to get this code commit put in. So what this will actually allow you to do, if you can control these values, it will allow you to respond or catch a response from the server with up to 64 kilobytes of random server memory, outside of the bounds of which should normally be accessible. So just a little bit about how SSL works. Typically, when it first starts, you're going to have a TLS handshake. So they're going to say, hi, I'm the server, hi, I'm the client, how you doing? We exchange some keys, and there's several steps involved. Now you have this TLS connection, this secure connection. Now, sometimes this connection is lost. Either lag or a dropped packet, some sort of network interference. You close the tab on the browser and reopen it back up. You'll end up with a situation that has many, many, many simultaneous TLS connections going between you and the secure website that you're on. And this is very heavy on the server. It's very computationally expensive. So this is where the need for this heartbeat kind of paradigm came about. We don't need all these matching TLS sessions. All we really need is a small request that goes to the client and a keep alive response that gets sent back. If that response comes back, you know, hey, this client's still alive. Keep the TLS session open. Now, in 2012, that's exactly what was, I basically said this slide already. Now, this heartbeat request is going to contain a couple things. It's going to contain the payload and the size of that payload. But it's all, the payload, size of the payload, plus a little bit of padding, and then that's what you're going to see coming back from the response. But we can craft this to be whatever we want. So say, if we're going to exploit this, we send a heartbeat request to the server. Now we're going to say that the payload is 1 byte, or we'll actually send 1 byte. Now the size is typically the same size as that payload, but we can lie about that. We're going to say that it's 65,536 bytes. What's going to happen here is once this gets stored in server memory, the little black text I have here, the P, that's the 1 byte that we actually sent. Everything in red is going to be referenced by the 65,000 bytes. So once this heartbeat response actually comes back, that's going to be returned to you as the user of the website. Are you kind of getting a feel for what all we can have access to now? There can be a load of things in server memory. Credit card data, login information, anything from a previous past post request that has been made to the web server. Cookies, passwords, CSRF tokens, authentication cookies, the SSL keys used to encrypt and decrypt traffic. So if you're actually, say you exploited this, and you have to send billions, or maybe not billions, but about 8 billion requests, because you're going to land on some arbitrary piece of memory, and you're limited by the amount of size that you can get back. But you can do this as much as you want, as unauthenticated as you would like, and it's kind of like a game where you're just putting together pieces of the puzzle. You'll get one chunk of the SSL negotiation keys, and you'll get another one. And you keep doing this until you have all the pieces. If you happen to have been logging traffic, you can then use those keys to decrypt past traffic if perfect forward secrecy wasn't used. Although it's around and baked into some versions of SSL and would mitigate that particular attack, it's not actively used, sadly.
I'm so sorry.
All right.
Oh,
Yep.
yes?
So we'll just wrap up. Yeah, no. So
Yeah.
the guy before us went 20 minutes over. Come on.
No problem. We'll try to catch up.
Okay, this is the last slide, promise. So just want to thank the community for submitting all these things, right? And if any of you voted on that, we appreciate that too. If you haven't, we'll do this again next year. You can vote on it then. So just some lessons learned. Encryption is still king, right? Heartbleed took took over the top slot. Encryption research is really hard to do, and the community realizes that. Creativity is super important. A lot of these bugs have been sitting around for 20 plus years, right? And it took just some creativity to look at it a different way and exploit it. And just web security prevails, right? Of all the security news that makes it into the major news headlines, it's always web security, data breaches, SQL injection, things like that. So web security is still king. So yeah, just want to thank you guys. We don't have time for questions or anything like that. You can find our Twitter handles on the bottom. You can find us in the hall after this if you
I'll be
want
in
to
the
ask us
CTF room
questions.
today and tomorrow. So
I just want to
just
thank
grab me.
the expert panel of judges at the top here. These are the guys that actually picked the top 10 for us. So thank you, everybody.
Thank